have is a video from Tonći, and it is more than 40 minutes long, so it just fills the entire slot. So I'll stop. I'll not talk too much. Tonći is from Amsterdam. He's a long-term community member. He's running a very thriving user group in Amsterdam, and well, he's here to talk about WebAssembly. And without further ado, I will start the video. So enjoy.
Hi folks, I'm happy you have tuned in today. Unfortunately I can't see you, which is for me a weird way of giving a talk, because normally I can hear myself, I can see people's reactions, etc. So this will be a little bit well, weird. I'll have to get used to it, so I apologize if this feels weird, but well, I'm happy that we can still that we live in an age in which we can do these things remotely. We can still connect and learn from each other, and do these kinds of things. So my name is Tonći Galić, and I work as a software consultant for Moose Code. So that means we help clients build scalable software by using Elixir, and one of our open source contributions is Horde, which is perhaps the reason you have heard of us. But today I want to talk about WebAssembly. And the outline of today's talk looks a little bit like this. So we'll first start by looking at what WebAssembly is and how it came into existence, why was it created. Then we'll dive into what WebAssembly is a little bit into more detail by writing our own very elementary interpreter. And lastly, we'll talk about what a WebAssembly can be used for. So why should we even care? So you might wonder, why did I choose this topic? Well, this was one tweet that I found interesting, and I hope it raises your interest as well, which is a tweet by Solomon Hykes, who's the CEO of Docker. And in this tweet, he basically says, well, if WebAssembly was created like 10 years before it has now, Docker wouldn't have existed. So that sounds very interesting and promising. And secondly, last period, it seems like WebAssembly is a little bit hyped. A small proof is the Stack Overflow survey from last year, from 2019. In which WebAssembly is pretty high on the list of the most loved, dreaded, and wanted languages. Well, it's on the most loved list, but it's a little bit weird because WebAssembly isn't a language. So to me, this reads as if it's a sign of interest, like people want to use or would like to use WebAssembly, rather than what people actually use and love using. So when I started working as a web developer, we could only use HTML to build websites. Yes, we did use CSS to change some background colors, and yes, we did use JavaScript to make some menus or to have text scroll around. But it wasn't actually until Gmail, or until Google came with Gmail, the people actually started using JavaScript to build full web applications. And ever since Gmail took off, folks have been trying to find ways to build richer and faster web applications. And Mozilla and some other major companies, they came up with a new compilation target called WebAssembly, which is now the fourth officially acknowledged by W3C technology for web applications. So next to HTML, CSS, and JavaScript, each browser nowadays also supports WebAssembly. And many other companies have tried to build such a technology to get it officially recognized. So you might remember ActiveX, Flash, Java applets, Google native clients, etc., etc., etc. They all failed in that, and now WebAssembly is the only one, or the only new addition to this stack of technologies that can be used on the web. And there are officially acknowledged by W3C. So I think that says a lot about the potential or the significance of WebAssembly. So what is WebAssembly? Well, the official term says that WebAssembly is a binary instruction format for a stack-based virtual machine. It is designed as a portable compilation target for programming languages, enabling deployment on the web for client and server applications. So that means just like with the Erlang virtual machine, people can use different languages to compile to bytecode, which then will be later translated into actual machine code. So with WebAssembly nowadays you can use different languages like Go, Rust, but also soon Elixir and Erlang itself to compile to WebAssembly. And I think even nowadays COBOL is supported as a compilation source to WebAssembly. And if you haven't heard about Lumen, Lumen is a project by Hans Elia Bekoms-Josephson, Luc Imhoff, Paul Schoenfelder, Brian Joseph, Brian Cardorella, and some others to try to write a compiler which takes Erlang or Elixir source code and compiles that to WebAssembly so it can be run in a browser. So with WebAssembly you have two formats at which we will look at today. Well, shortly at least, is the WAT format, which is the WebAssembly text representation. I think they should have called it WebAssembly text format, W2F, but the file extension is WAT, WAT. I think they missed their chance there, but okay. And WASM is the binary version of it. So once it is compiled into this WebAssembly binary format, it gets the extension WASM. So let's get enough talking. Let's get coding. So we'll start by creating a new project, which we'll call Wembly, short for WebAssembly. And I'll copy some files like the one that we're going to interpret. So on the right we have the text representation, and on the left we have the how do you say it? The same version, but then in Elixir and Erlang. So if you have trouble parsing what is on, I think you're right, on this side above me, then you might want to read the other side. But anyway, it doesn't really matter. This is like the example we're going to use, and it's is a module to calculate the nth Fibonacci number from the Fibonacci sequence. So it basically looks if the n is smaller than 2. If so, it will return 1, and otherwise it will calculate, like recursorily calculate Fibonacci by doing n minus 2 and plus n minus 1. So let's delete this code, and we'll start by writing a test. So our first step is to actually read the WASM file and make sure that our program doesn't crash. So reads WASM file, and we'll do use a file for that, fib recursive, which we just copied over, and we'll try to read this file, and the result of reading in this file should be a tuple saying okay, some binary, so the stuff that we've the binary content from the file. So let's see if we didn't do anything wrong. No, fails, that's good. So then we'll start by writing our function. Our import file function will take one parameter, a path. So it's basically path to the file that we want to read. And we'll use a bit string to check for the magic string. So most most files nowadays also have something called a magic string, which basically helps the operating system to recognize what kind of file it is. So if you ever open the PNG in your editor, you'll probably have seen somewhere in the beginning of that file also the words PNG. Same for pkzip, package zip, if you ever open a zip file, a JFIF or XZIP for a JPEG, etc. And WebAssembly in our case starts with 0asm, followed by the version number of WebAssembly, which is nowadays 10, so in this case 1000, because they probably expect more versions. And yeah, let's see if our test succeeds. It fails. Oh yeah, of course, because we forgot to return a tuple instead of the whole content of the file. So let's fix that. Then we should have one succeeding test. Yes, cool. Okay, so next, our final step is actually to make sure that we can run this function, this Fibonacci sequence. So we'll calculate. We'll first read in the file itself again, like in the last test, and then we'll actually see if the fourth Fibonacci number is actually 5. So by running the code from the WebAssembly module, we should get 5 back as a result. And yeah, that's okay. So let's start writing. So first, we'll write the struct for this, which holds all the information about our module. So each module has a name, has a stack, has some type information about it, so which types are used by which functions. Yeah, there is more, but we'll skip that for now. So we'll start by writing our apply function, which takes current module that has the code, the name of the function, which doesn't matter because we only have one function. We'll just skip this for now, and the arguments for that function. And then the result, we'll take the result stack from running that. So whatever the result was after running that function. We only have one function, so we can use just the head or the first item from the functions list and apply the arguments plus the stack. And then we'll look at what the result of the stack was and return that as our end result of applying that function. Our next step is to start parsing the file. WebAssembly modules, they are built up from different sections. And you can read all about that on the website of webassembly.org. Somewhere in the head they have a link to the specs, and you can read all about the module, what kind of sections it has, like function sections, which describes which functions we have, what kind of types they hold, etc. But for today, we're only interested in the code section, which holds all the instructions of a function. So, like WebAssembly is a binary format, instruction format, which and our each function in that module is translated into instructions, and we'll basically be reading out those instructions and execute the code by that. So this is if you open it as a binary format. If we look at it from a hexadecimal side, then it looks a little bit nicer to read. So you can see that it starts with 0, followed by ASM assembly, then the version number 1000, and from there it has different sections. So 01 probably stands for functions, I think, and 03, which is 2 bytes long, and 07, which is 7 bytes long, etc. And then later on we have OA, which stands for the start of the code section. And this is basically what we're going to parse, what we're going to work with today. So in here you can also read that it is exported by the name fib, so other modules can look it up. So yeah, let's start reading that file. So we'll start with parsing different sections. So our parse section function will take the instructions, so the binary format, the current module, and then we'll slowly step through each of those parts to then return the actual module that we have parsed, that we are going to use to execute code. So once it is done, the list of instructions is empty, and we return a tuple saying OK module. And then we can continue by reading the first part, or at least not the first part. We're going to look at the code part, which starts with OA and some length, which will treat as an unsigned integer, which basically the second byte specifies how long it is, followed by the instructions, which has the size of L, and then the rest, which we'll parse later on. So, and each code section also can hold different functions. In our case, it's just one. We know that, so we can kind of skip some parts and not care about it. But it could happen that one code section holds information about holds instructions for more than one function. So that means once we're done with parsing a code section, we could have parsed multiple functions. Next, we'll parse the other sections, which have an ID, some length, followed by some section contents, which we don't care about, and the rest of the WebAssembly binary, which we will discard. Well, we'll discard this section actually, and continue with parsing the rest of the sections. So let's save our efforts. We made an error. Keyword followed by types. Of course, need a space between types and the start of the empty list. So let's see what else we forgot. Okay, yeah, good. We're good on our way. So once we have parsed all the sections, we're going to run our function. And the run function takes the current module, the instructions it has to run, the arguments and the stack, and any locals, meaning local variables basically in Elixir. Well, locals in WebAssembly is kind of equivalent to variables inside a function in Elixir. So as a first step, as a first start, we're going to take the arguments from the stack and add it to the locals list, so we can use it as local variables. Then we'll actually continue by running the rest of the instructions. And each time as we go through run function, we return a new version of the module with an updated stack. Oh yeah, we made a promise to return the stack, not the module. So yeah, let's change that. We'll cheat a little bit to make our test pass. Yay, we're done. No, just joking. So this is basically what the result would be. So after running all the functions, we get the stack, which only holds one number, in this case 5. So if you ever have to work with WebAssembly, there are different tools which help you to read the files. So let's take a short look. One of them being WASM object dump, and you can use it to inspect different sections or to do a disassembly of the code, so you can actually take a look at what instructions and function actually holds. So let's take a look at the sections first. So in here you can see the contents of the specific sections and where you start, etc. So let's put that next to the actual contents of the WASM file in the same hexadecimal encoding. So you can see here that the contents of the type section corresponds, the type section of function also corresponds, so it's 03, 2 bytes long. 07 is the export, which contains the reference to the Fibonacci function named fib. Then after that we have the code section, so it starts with O1, 1D, etc, etc, and it ends by OF, OV. So let's look at the disassembly, so the instructions itself. And this is basically the code part that we have under the functions key of our module struct. And we're going to now basically run those instructions, to interpret those instructions. So in this part we parse the code section of our module, and as I mentioned, each code section can have multiple functions, but we didn't take that into account. So let's start parsing the individual functions inside a code section. So the result of our parse functions is a list of new functions. So once we're done, we'll return all the parsed functions. And each function section starts with a count of the functions, the size for the contents which we need to extract our function, and then the rest of the code section. Each function starts with the locals count or locals amount, so you know how much memory you need to allocate for the various variables, followed by the actual code, the actual instructions, and that's also the part that we're going to accumulate in return. Next we can, nicely formatted, next we can continue with implementing our run function. So we'll replace this by the actual work that we need to do. So after we're done with going through all the instructions, we want to return the result, so basically implement our exit strategy here. We don't care about locals, a state, or whatever. We just want to return our stack, which is list. Next, we'll let's see. Yeah, we'll start by running the first instruction, which is getting the first local 0 onto the stack. So we'll implement the function run, which takes the current module, the instruction to get local, which you've seen is 020, followed by the index of the local, which, because we have a list of locals, we can get to them by using the index, followed by the rest of the instructions, stack locals, and the state of our interpreter. And we'll basically get the needed local from locals list and add that to our stack. So after this, we're going to look at the next instruction, which is add constant to the stack. So we're going to write a run function, which takes a module, the next instruction, which is 41, and the number that it needs to add to our stack. It's num. And the rest of the instructions, which we'll parse later on, or run through later on, sorry. We're not parsing anymore, we're running code. So it will basically add the number to the current stack at the top of it. And continue with parsing the rest of the instructions. Next instruction is to compare if A is smaller than B. Basically this instruction, number 48, takes the first two items from our stack and compares them together, and actually tells us if A is smaller than B. No, I meant it the other way around, if B is smaller than A, yes. And we'll cheat a little bit by returning, well, by putting true or false on the stack. That's not how, by the specs, the WebAssembly interpreter should be written, but, well, we'll call it a little happy little feature in this case. It works for us, so I don't care today. Next, this is going to be interesting. We're going to go through the if expression, and you'll see that the if actually takes two instructions, 04 saying it's an if, and 40, and 40 is actually the it denotes that this the type of this if block. But we don't care about types in this case, so we'll skip that. We're just going to look for the if instruction, which is 04, followed by some type information, which we don't care. The rest of the instructions, which we'll parse, which we'll run later. Keep making that mistake. And then we have the boolean of the previous instruction, and we'll use that to go either through that if expression or around it. So in here we'll change the state. So if it is true, then we need to continue running, and else we need to go to the end of this if block. So we'll continue running, and based on the state we'll go either left or right in this branch. So made a mistake. Of course. And there's no, because, oh, we're not adding anything to the stack. Okay. Okay. So what did we miss? Okay, yeah, still needs to be a symbol. Okay, cool. So, an atom, sorry. Too much Ruby in my days. So let's continue. The first part of the if adds 1 to the stack. We've already done that, so we can skip it actually, and continue with the following one. If, which is the return part. So this means that once we reach this point, our function should return and shouldn't read any more instructions and just return whatever we have on the stack. So we're pretend we have reached the end of all the instructions and finish that. So let's see, we made a typo somewhere, I think. Oh, we don't have a module. Yeah, okay, it's mod. So let's see how far we got. Okay, just still pass. Let's continue. So next we'll continue with the logic of running code and skipping through the end of the if block. So if we reach the end expression, it means that we can continue running our code. So it means we're at the end of the if block, and we can stop skipping instructions. So that means we turn the go to end state into the run state again, and we continue running code. And in the case that we have some other instructions and we're still in the go to state, that we skip that instruction. Stack locals and run. No, go to, yeah. So that should take care of the if block. Next, we'll continue with local get. We already have that. Subtract B from A in this case. So the instruction is 6B. We take the rest of the instructions and the first 2 items of our stack, and we basically calculate B minus A and put that result on the stack again, and then we can continue with running the rest of the code. And after that we have the call. So we call ourselves again, and this is where we use the index number of the functions to know which function we have to call. But in our case we only have one function, so we actually, well, we would need this index, but we'll just pretend that we're good citizens and we'll follow the specs just this one time. So we're going to take the instructions from the functions lists at the index, and we're basically going to start that function again using the stack current stack and start state. Let's see. And then we'll basically, after that function has returned, we have a new stack, and we'll basically continue running our code, our instructions with the new stack. So then local get, we already done that, subdivide did that, call did that, and then the last part is to add. So that means we're going to handle adding two numbers together. So we'll take first two items again, rest of the locals, the state, and then we're going to return a new stack which A and B combined. Save that. And we made some errors, I think. Is unused. Ah, okay. And we find module mods should be, yeah, okay. And A is unused because, okay. And this function clause is not needed anymore. And I think we're good to go. Let's see. Function clause in WebAssembly 5. Line 12, I think. See our list. This is nice, live coding. I think we'll take a look at line 12. Oh, of course, we haven't used functions. Okay, so return a list of functions, so we don't need this anymore. It's already a list. And is that it? Yay, we're done. So let's do a test run. We'll import the file first, get a module back, which we then can use. Make sure pip recursive.wasm. No? Okay. Fixtures. Makes sense. And then we can use that module. Apply. Well, it doesn't matter actually, but okay. And let's do 1. Returns 1, 2 returns 2, 3 returns 3, etc. And yeah, you can check this at home. This works, but I think it should suffice. So a little bit more time to talk about what we can use WebAssembly for. I'll go over this shortly. I have really little time. So some examples of using a virtual machine inside something else, which is basically what WebAssembly is meant for, to be used inside other projects. Lua is known to be used inside games. So normally games are written in C or Rust or something that's really fast. And if you want to make your games more scriptable or more easy to adapt, then people have used Lua to embed small scripts or small parts, so small contents inside their games. Linux also uses the extended Berkeley protocol filter, I think is used, yeah, which helps you write code that has basically the same reading access as modules inside a kernel, but cannot wreak havoc because they cannot modify things. So it can be used to actually have code that usually resides inside a kernel to have it run inside user land, but then in a safe way. So basically have some safe way of accessing kernel information. GraalVM is an example of using a virtual machine inside something else. And of course, probably the most famous example is JavaScript. But JavaScript is an interpreted language. It's not that portable. People, at least machines, first have to parse it, turn it into an AST, compile it, run it, and then later on try to optimize it by using a just-in-time compiler, etc. And WebAssembly kind of skips a lot of those tests by going into a binary format, into a compiled format straight away, making it much easier and much faster to run inside browsers. So yeah, what are some use cases? you could use it to safely use external libraries or languages of modules. JavaScript is, well, I shouldn't bash it, but we have seen examples in other languages like JavaScript, which had a lot of problem in which a module or a library had access to the whole file system instead of just parts of it, instead of just the parts that it needed. And by using something like WebAssembly, folks want to prevent that because WebAssembly needs its host. So it's WebAssembly runs, in this case, runs inside a host system, and it's a guest, and it cannot just go and access files or whatever. There are no instructions currently to access the file system. It needs functions or functionality from the host system to do that. You could, for example, also use it to safely share code between front end and back end. So I don't know, make isomorphic functions, or for example, accept input from users. So if you have a chatbot and you allow your users to script those bots, then they might get used to writing code, but you don't want to straight away to execute that code on your backend. And by compiling it to WebAssembly, you can have a safe in-between bytecode that you can execute. And WASM could be used, in the case of Elixir and Erlang, could be used to have faster number crunching, but it depends on what kind of backend or runtime you use WebAssembly with. And what are some drawbacks? It is a standard, but it has a lot of conventions, so implementations could deviate. It is also very much early stage product. It's 1.0, but it has a lot of things people want to add on before it really catches on. It doesn't have any concurrency model, it doesn't have garbage collection. They're still working out how they can share type information between languages, which is also the kind of last point in this slide, is that mixing languages might not be that easy, because one language might store strings in a way, and another language might do it in a different way, and then you'll get error because those two languages cannot safely share a string. So if you made it this far, hats off, well done. If you have any questions, my name is Tonći Galić. I'm on the internet. I use the handle Toxified. You can also send me an email. And I hope you enjoyed the rest of your conference, and stay safe. Bye-bye.
Yeah, and of course you can also ask questions on the Wahuba app for this session. And I think we're a bit over time, so we need to open the next track or the next presentation. So yeah, thank you for attending.